Hello, everyone. Thank you so much for joining us today for our live session. We are excited to have you here. And my name is Matthew, and I am one of the instructors for our online classes. Some of you probably are from those classes. Others are from just finding out about us through other media, other means. I'm going to hand this over to Professor Impey, who's going to welcome you, and then we will get started right away with your questions. Make sure you post those in the chat. We will grab them from the chat and ask them live on the stream.
Okay, welcome everyone. It's of course, been a tumultuous week or so in the United States where I am. Many of you are not in the United States, probably have been watching in amazement and horror at what happens here. But out in the world of astronomy, things are very calm and placid and discoveries continue. So we can just talk about that. So welcoming your questions starting now.
Excellent. Our very first question today is going to be from an email. The question is about wavelengths and the spectrum of a star. If you analyze the spectrum of a star, are we able to, basically, can you explain how we are able to find information out about stars from absorption lines and Doppler shifts and things like that? Sure.
So understanding stars, that's a very foundational part of the history of astronomy. And most of the insights and the discoveries happen in the early part of the 20th century. These are some very famous stories in the history of astronomy. Basically, the power of spectroscopy is its remote sensing. It allows you to sense physical conditions in a remote astrophysical object, and stars are the best example. So people had taken spectra of stars, well before the turn of the 20th century. Wollaston and others, Fraunhofer took spectra of the sun, the brightest star, of course, and these narrow absorption line features were seen in the sun, and it was recognized they corresponded to chemical elements. And through the 19th century, it emerged that some of the lines were unidentified. Others could be identified with the major elements, hydrogen, calcium, sodium, nitrogen, and so on. But there were lines that were unidentified, and actually the first detection of helium was not on the Earth, but was in a star, because most stars are made of hydrogen and helium primarily. So it was realized by the turn of the 20th century that spectroscopy was a very powerful method for deciding the chemical composition of a star. But just measuring the lines in a star doesn't really tell you enough. And so what happened in the first part of the 20th century was foundational research, primarily by Celia Payne-Gaposchkin, astronomer, a very pioneering woman astronomer at the Harvard Observatory, who developed the physics and astrophysics method by which to turn measurement of spectral lines into a physical model or understanding of the star, because these lines are produced in the outer cool layers of a star, whereas the central core, the fusion burning region, is not directly observable by optical telescopes. So you actually have to make a model for a star by which to interpret the spectral lines you see. Now, not only are the lines identified with elements, but the width of the lines tells you something about the temperature and pressure in that outer region of the star. And so those are keys to understanding the structure of a star. And by the 1930s, Eddington, Hertzsprung Russell, and other astronomers used all this information to produce the first robust model of how stars work. So spectroscopy of stars is foundational in understanding how stars work, that they are fusion engines, and what their structures are, and what the different types and masses of stars are, and how they live their lives.
Excellent. Thank you very much. The next question is from Newtopia, who's on with us live, who would like to know if you think that the next American administration should continue with the Space Force, and does it have anything to do with astronomy, or is it entirely military?
Yeah, the Space Force has been fairly controversial amongst in the scientific community. Many scientists just didn't feel that it was a necessary thing, and if they did indeed see that it was primarily a military entity and so not going to help with research at all. And it's, of course, it was done without proper funding from Congress by action of the administration. And the truth is, it's not very heavily implemented at this point. It's not a major branch of the armed forces at this point in terms of funding. It's not clear. The new administration has not transmitted their intentions with regard to Space Force. They have so many things they're dealing with, pandemic, economy. I think the Space Force is pretty far down their list of priorities. But of course, it will get their attention. And I suspect the Space Force will essentially just go away or be subsumed into the Air Force or one of the other major forces. Now, the legitimate concern driving the idea of a Space Force is, of course, a national security concern, that there is a worry about the militarization of space, particularly regarding the Chinese, who have quite secretive and advanced plans for space activity where the military intentions are not easy to discern except using intelligence agencies. So that's a legitimate concern, but that on its own, given that other federal agencies also worry about military surveillance and do it, it's not clear that that alone justifies the Space Force as it was originally conceived.
Excellent. The next question is from a live viewer. Mira Switzerland would like to know, our universe is expanding. Is it fair to assume that therefore our solar system is proportionally expanding? If not, why not?
Right, so the expansion of the universe does not equally affect every scale in the universe. So that's an important caveat to put on the expansion of the universe. Everything is not expanding. I'm not expanding, the room I'm in is not expanding, the Earth is not expanding, and the solar system is not expanding because the gravity of the sun binds the planets to the sun. They're gravitationally bound. And so energetically, they're maintained in stable orbits and are not expanding. And that is also true of the galaxy itself. Because of the influence of dark matter, our Milky Way galaxy and all the other galaxies we can see do not seem to be expanding. They will be roughly stable on long time scales because they're bound as entities by their mass and particularly their dark matter. And so everything up to the scale of a galaxy is essentially not expanding. Beyond that, the galaxies are embedded in space-time, and it's the space-time itself, the fabric of the universe, if you like, that's expanding. The expanding universe refers to the space-time manifold. That's a mathematical term, but it is a mathematical theory of general relativity that describes expanding space-time. And essentially, the space-time itself is expanding, but the objects that it contains might not be expanding because they may well be held together by their forces, thereby molecular forces in the case of a planet or a person, or by gravity in the case of a solar system or a galaxy.
All right, the next question is from W Subtle 7. Olympus Mons is 21 kilometers high. Why doesn't it sink back into the mass or the surface of Mars?
That's a good question. There is a natural principle that applies to rocky planets, which is that there is a natural maximum size to planetary features, and the physics of this is fairly easy to calculate. Freshmen do it, for example, as an exercise. You can actually take a mass of a mountain and a height, and you can work out what the pressure is at the base of that mountain, given the mass of the planet and its gravity. And you can work out the height at which a sort of a triangular profile mountain will have a pressure at its base sufficient to melt the rock that it's made of. And at that point, the mountain should not grow any higher because it will essentially extrude liquid rock at its base and just not grow anymore. If you do that calculation, it also depends on the gravity, of course, and so that will be a different calculation on the Earth as it is on Mars with less gravity. And so when you do this calculation on Mars, it turns out that Olympus Mons is not even that close to this limit. You could, in principle, have mountains on Mars that were 50 or 60 or 70% higher than Olympus Mons before you'd have this issue where the pressure and heating would liquefy the rock and stop a feature from growing anymore. So that's why Olympus Mons, although surprisingly high and larger than any mountain on Earth, does not violate any physical or geophysical principle.
Charlie Hollis, who's on with us live, says, how would you respond to the arguments from Eric J. Lerner that there was no Big Bang. Apparently, he has presented work at the American Astronomical Society meeting showing that the Big Bang theory of the origin of light elements doesn't work out well with the abundances of lithium and helium.
I would say that for people who want to have an alternative theory to the Big Bang, I would say the bar on evidence is very high because, and the thing you really have trouble explaining with any alternate theory is the microwave background radiation. So regardless of the issue of the light elements, which I'll come back to, the Big Bang is in sturdy shape, I would say, because we observe an expanding universe, so we can project backwards to a time of higher density temperature, which is what the Big Bang was, and we can see the relic radiation left over from this early hot, dense phase. That's very hard to explain any other way. It is true that the evidence from light elements of a phase of the universe in the first few minutes where fusion occurred in the entire universe, creating light elements, that evidence, some of that evidence is ambiguous. But of the light elements that are under discussion, it turns out that lithium and helium, the two that Lerner alludes to, are indeed they're the less convincing of those light elements in terms of uniquely pointing to the Big Bang. Lithium is difficult because it's created and destroyed in stars. So it's very difficult. You have to know a lot about stellar evolution to be able to pinpoint how much lithium was created at the origin of the universe and how much lithium might have been created and then partially destroyed since then. And so I think lithium is a bad indicator of anything about the universe just because of its role in stellar evolution. Helium is a different case. Helium indeed is an important element, and one in 9 atoms and a quarter of the universe by mass of normal matter is in the form of helium. Now, typically the way astronomers match to the Big Bang is they look for the most primordial galaxies, the oldest, most unevolved, chemically unevolved galaxies they can find, and they essentially extrapolate back to a sort of zero abundance or sort of zero stellar evolution and mixing of chemical elements in a primordial galaxy, and that should be the helium that was produced early in the universe and then became part of the galaxies. That matching to the Big Bang model is pretty good, actually. Now you can do it in different ways, and it's a slightly indirect measurement. So Lerner, I think, is pointing to limitations of that analysis. I would, however, point to the best indicator, which is deuterium. Deuterium is an isotope of hydrogen, and it's heavy hydrogen essentially, and it is abundant only in the intergalactic medium. And so the measurement of helium occurs in the voids of space where there's no stellar processing, no other astrophysics going on, very low density regions, and it essentially points directly back to the early phase of the universe. So the deuterium abundance, about 1 part in 10 to the 5 of hydrogen, matches extremely well with the Big Bang model. So overall, I would say the Big Bang model is supported by the abundance of light elements.
Excellent. Thank you very much. Megha Sharma sent an email asking, what role does quantum tunneling play in stars?
Quantum tunneling plays an essential role in stars. In fact, if you try to do the calculation of stellar fusion, how the sun works, for example, how the sun shines, you will fail in this calculation unless you include the process of quantum tunneling. And essentially, it goes like this. For fusion to work in any star, you are essentially forcing protons to merge together to eventually form a helium nucleus, 2 protons, 2 neutrons. The protons are positively charged, and so they have a Coulomb or electrical repulsion, and that repulsion goes up as they get closer. And in principle, that repulsion becomes infinite when they get sufficiently close. So to make protons fuse or stick together, you have to overcome this enormous electrical repulsion from the Coulomb force. And if you do the calculation with classical physics, it doesn't work. In the temperatures pertaining in the center of the sun, you never actually create helium at all, or very, very small amounts. What happens, however, is that the quantum tunneling calculation, aiding and abetting your understanding of how the center of a star works, leads to the fact that there is a non-trivial, a very significant probability of the protons sticking together and then on up the fusion chain. And so quantum tunneling is an essential ingredient of understanding how stellar fusion works. And then therefore it's a success of the stellar fusion model and also an affirmation that quantum tunneling is a real effect.
Excellent. The next question is from student McLeod. If professional astronomers at an optical observatory site were hoping to show off for potential donors, is it possible to put an eyepiece in one of these large telescopes, and what kind of eyepiece, what design of eyepiece would they use for something like that?
That's a good question. And indeed, for donors and prospective donors, and sometimes for political leaders or very high-ranking officials in the country of the telescope. For example, Chile has telescopes and the government officials visit them. Yes, they often want to look through the telescope. Just taking a picture with a CCD camera is not quite the same thing. It is difficult, actually, for many telescopes, especially the largest telescopes, to simply put an eyepiece into play. And that's because the instruments that sit at the bottom, typically of a telescope at a Cassegrain focus, are essentially usurping the light path. And there's no simple way to modify these instruments to put in a little pick-off mirror, an angled mirror that might deflect the light out to an eyepiece. However, some of the telescopes do have instruments where this is possible for diagnostic purposes. So if they have a visitor, they can put the appropriate instrument on, which will be one of the rare ones that lets you put in a little angled mirror and pick off the beam of light and then through an eyepiece. Now, actually, some of these big telescopes are so large that to do this for a bright object like the moon, I mean, that would blind you essentially. So you can't actually show off something like the moon without putting a huge number of neutral density filters and essentially taking the light down by factors of hundreds of thousands or millions. But you can do dark sky observing, and I've witnessed this several times. Once on Mauna Kea at the Canada-France-Hawaii telescope, the science minister for France was visiting, and I was there observing while the science minister sort of took over the telescope for an hour in the middle of the night, and they put in an eyepiece and let the science minister look through the telescope. Also, a little story of my own from observing when I was a postdoc at Caltech. I and a polarimeter expert from Arizona, we had a traveling instrument that we put on the 200-inch, the Palomar 200-inch, also called the Big Eye. And that, because it was a traveling instrument, it was used to be used on small telescopes where you did actually look through an eyepiece. And we put it on this big telescope where the eyepiece was still there. And so one cloudy night, not quite cloudy enough to be opaque, thin cirrus basically, but too cloudy to do good astronomy work, we got to use the 200-inch on Palomar Observatory to look at the moon, at planets, at star clusters for an hour or so. It was a pretty amazing experience.
Excellent. I also have been able to look through the telescopes at Mount Wilson Observatory. They do have some eyepieces that they let people put on there, and that's pretty spectacular. Robin5660 has a question, and we can probably talk about the premise of this question a little bit, but can you talk about why time is different across space?
Well, the relationship between time and space is an important issue in astrophysics. And essentially, it derives in the modern understanding of the universe from general relativity. And in general relativity, space-time is a hyphenated entity. It's essentially 3 dimensions of space and 1 dimension of time, and they're coupled. They're mathematically coupled. And so perhaps the best way to think about it is that these things are not distinct. And so the nature of time can be connected to the nature of space. For example, if you have very high mass energy density, and so you have space curvature as one consequence, and you also have time dilation, or slowing down of time, as a second consequence. So the nature of time and how it flows does depend on physical location in the universe and depends on the local density of mass and energy. And that's a straight prediction and a verified prediction of general relativity. So that's really how space and time are related, through this mathematical theory of gravity called general relativity.
The next question is from Salse1. For an eventual society on Mars, do you think Mars should be a free planet?
Well, Mars is a free planet. The there is no jurisdiction of any country or the United Nations or any intergovernmental body beyond the Earth. And so as we speak, Mars, which has been subject to space exploration and space probes from a handful of nations, is not owned by anyone, is not governed by anyone, nor regulated by anyone. It's not clear what the validity would be if humans eventually go to Mars of some country or some entity, could be a corporation, declaring that they own some part of Mars. If that were ever litigated, it's not clear how it would be litigated, the World Judicial Court, I suppose, it probably wouldn't be upheld. So at the moment, Mars is a free planet in the sense that no one has the right, which could be defended in any court on Earth, to declare ownership or purview over some part of Mars. Now, the point, of course, of all this space law is that none of it has ever been tested. And there's a very thin amount of space law compared to the amount of law on Earth. So it seems like as we develop the space activity, there's going to be the emergence of this space law activity, which is after going to create a sort of infrastructure for resolving disputes. What if two entities, two countries, or two companies go to Mars and want to mine the same area or colonize the same area and come into conflict? Who will resolve that conflict? So if space is not going to be a Wild West and a completely lawless place, we're going to have to develop some new protocols and some new legal structures, and they're going to have to be enforceable. And enforcing law off Earth is going to be a very interesting proposition.
All right, this next question will test your astrochemistry a little bit. Hernan Reyes, who's on with us live but also sent an email, has a question about Titan's atmosphere. In particular, solar photons react with the little bit of methane, CH4 molecules, to photodissociate them into other organic molecules. One main product should be acetylene, which is C2H2. But apparently this has never been found on Titan. And so his question is, what replenishes the methane in Titan's atmosphere? Because we keep detecting methane, but it should have been broken up by solar photons.
Right. That's a good question. It's a fairly high-level question, but Hernan has always high-level questions for us. Acetylene has not correctly, it's been not detected in Titan's atmosphere. It has been detected in Venusian atmosphere at a very low level. So we have seen acetylene in a planetary atmosphere. However, we've not seen it in the atmosphere of the moon, Titan. What is suspected is that the methane is simply replenished on a short time scale. The other thing we know about methane is that it does dissociate. In fact, it has a very short lifetime in a planetary atmosphere subject to solar radiation. It's hundreds of years, maybe 500 or 1,000 years maximum. For example, that's one of the reasons why in Mars work, the presence of methane in the Mars atmosphere and its variability has been considered a potential biomarker, because that methane will disappear quite quickly. So it has to be dynamically replenished, and the speculation is it was replenished by biological activity under the surface. Now, in the case of Mars, the concentration of methane, few parts per billion, is so low that that could be done by geology, by active geology. It doesn't have to be biology. In the case of Titan, Titan is subject to cryovolcanism. So we know that the conditions, Titan is a fairly large moon. It has internal heating. It has tidal heating as well. And so we know that there's energy generated within Titan, which will percolate up through the core to the base of the shallow ethane-methane lakes and then release methane. So we think that energy release within Titan will create the processes by which the methane is continually replenished, and therefore you don't have to actually expect to see acetylene.
All right, the next question is from Kuchiko, who's on with us live. There's been a lot of news about the Starlink satellites are starting to communicate with people on Earth and test upload and download speeds. What do you think about Starlink? And in general, what do astronomers think about it?
Well, Starlink is a so-called constellation of satellites that's being put up. It's in the process of being deployed by SpaceX for the purposes of generating, high-speed internet in places in the world, developing countries, Africa and Asia primarily, where there's no infrastructure for ground-based internet or fiber or cable. So it's a very important thing in the world, in terms of world development, to give internet to places that don't have internet and high-speed internet. And of course, these are low Earth orbit satellites, and to maintain sufficient coverage, you need thousands of them because each one has quite low power, and so you have to lace your network in the sky with these transmissive satellites. The constellations are going to end up in the tens of thousands, a few thousand so far. And it's unpopular with astronomers because these are reflective objects, which when they catch the sun just after sunset and just before sunrise, they are very bright and they appear strongly in any image taken with a large telescope. And large telescopes have already shown that they're going to be a real problem for things like the Vera Rubin Observatory, the Large Synoptic Survey Telescope. So this is unpopular, and there's an ongoing debate between astronomers, their regulatory bodies, and SpaceX itself to try and mitigate that. So far, by using different coatings, more matte black coating for the satellites to reduce their reflectivity. That doesn't stop them from being observable, though, and they are really going to interfere with deep sky astronomy. There's no doubt about it. So it's a little bit of a standoff because SpaceX are not going to alter their trajectory as a company. They have a business plan and a motivation for doing this, and some of the reason for doing it is a good reason to make a more equitable world for the internet in developing countries. And astronomers are sort of collateral damage in this approach. It's also a significant amount of space debris. These satellites are designed to deorbit naturally after 5 to 7 years, and then they have to be continually replenished because they're in low enough Earth orbit deliberately that they suffer a very small amount of drag, and they eventually deorbit and burn up. So they are not a long-term threat once they're obsolete, because they will eventually all fall out of the sky. But for now and for the next few decades, they're going to be a problem for astronomy.
The next question is from Annie Ice, who's on with us live. Annie Ice 15. What do you think happened to the black hole in the Abell 2261 galaxy that is apparently missing?
Well, when a black hole, you expect to see a black hole. So let's drop back to the premise. This is a particular instance of a galaxy that should have a massive black hole and doesn't seem to, as well as they can measure it. The basis for expecting the black hole is a very strong relationship that's been seen now on hundreds, maybe thousands of galaxies, which is the proportional mass between a central black hole and the galaxy that contains it. In particular, the old stellar mass in that galaxy. And so that's a linear relationship that applies over 5 orders of magnitude. It seems to be some regulated process by which when a galaxy forms, it forms a black hole, and as the galaxy grows by mergers and accretion, the black hole at the center grows too. And we do see black holes in essentially every galaxy we look at. So we almost have to explain why either we don't see a black hole, or whether the black hole happens to be low enough mass that it's hard to detect. That's another possibility in this case, because we can only detect black holes with a certain mass threshold. In either case, something is needed as an explanation. If the black hole just turns out to be abnormally low mass for this size of galaxy and therefore undetectable, we'd have to explain somehow how this galaxy starved its central regions of gas, and so the black hole didn't grow. That, for example, could happen by a maybe slightly unusual history where the galaxy was continually swept clean of gas by collisions with other galaxies. Or because the star formation rate in the galaxy was particularly low. The other possibility, which is also testable, I think, in principle, is that you can have binary black holes or multiple black holes at the center of massive galaxies because, again, these galaxies grew by mergers, and as galaxies merge, their central black holes merge too. But it's possible in some of these merger processes that 2 black holes near the center of a galaxy, or 3, produce a slingshot mechanism where one of the black holes is ejected. It's given more than the escape velocity of the galaxy. And so that's possible. That's a way to eject one black hole. And in very low probability instance, you could have 2 black holes that are both ejected by such a process. At the moment, we don't know. So this is a bit of a puzzle.
The next question is from Millikan Nur Kolak, from our live chat. It was recently announced that a new quantum particle may have been discovered at Princeton University. Can this change something in astrophysics, and what does this mean in general for science, physics, and astronomy?
Yeah, I'm going to have to pass on this because I don't know what the discovery that's being talked about. If I had the name of the particle, I could maybe comment on it, but I'm not sure I'm aware of this particular discovery yet.
Certainly. The next question is also about Titan. One of the large liquid methane lakes on Titan has been found to be 170 meters deep by bathymetry. Can you talk about how bathymetry works on a planet as far away as Titan?
Right. Well, the fundamental tool for looking at the surface of Titan, which has a thick atmosphere, remember, it's thicker atmosphere than the Earth's, made of essentially pure nitrogen, is radar. So we go by radar through the atmosphere of Titan, and the reflectivity of the liquids on Titan does give you some sense of their depth as well. Also, you can see what the topography of Titan is. So it's pretty clear just from the surrounding topography what the likely depth of any lake that you might find is. So it's a mixture of, reflectivity, that the actual tool that detects this liquid itself, and the surrounding topography makes it a pretty reliable prediction of what the depth of a particular lake is. There is some uncertainty attached to it. I'd say it's about 20% uncertain anyway.
The next question is from a Lizard, who's on with us live. What do you think would be the biggest challenge facing people colonizing Mars?
I think the biggest challenge is really isolation. This is a brutally harsh planet, and so you cannot really be out on its surface. And so you're going to be in a contained habitat if you're a colonist, and that's going to have to be very efficiently designed. It can't be a super spacious dome like a football stadium or something like that. It's going to be a pretty cloistered environment where space is used very carefully. And you really won't be able to for example, be able to have nice translucent windows to look out on the Martian landscape, because that's dangerous in its own right for the security of the structure, and also for energy losses, and also for meteor impacts from the side or at glancing angles. So you're going to be in a darkened environment with artificial light and maybe artificial scenery put on a holographic display or something like that. And you really won't be able to spend a lot of time outside, because all the time you spend outside, even in a spacesuit, is unprotected, and you're going to take cosmic ray damage, and you're going to shorten your life essentially. So for the Martian colonists, just being inside and being so far from home or from rescue, I think is going to be an enormous psychological strain on the colonists, especially if they really are going to be there for a long period of time and not just for a 4 or 5 year stint and then they go home. If they are really going to spend their lives there and maybe raise families there and actually have a self-sustaining colony, I think the psychological backdrop to that is an extremely challenging backdrop, and it'll be only quite amazing people that are able to do it and willing to do it.
All right, the next question is from Theo Bernasconi, who would like to know, what is your opinion on what is outside of our universe?
I think, based on the standard Big Bang with expanding space-time and a horizon that is the limit to what we can see, which includes a couple of 100 billion galaxies, I think it's fairly safe to say that beyond our horizon, the visible universe is more of the same, that the space-time is much larger, especially if inflation is true, then the space-time of our universe is much larger than the space-time we can see with our telescopes, or which has had the distances which has had time for light to reach us in 13.8 billion years. So I think it's more of the same. In other words, many more galaxies, many more stars, many more planets, and maybe many more biological creatures out in space. There's no indication of an end or a limit to it. So that's basically my answer, more of the same.
The next question is from nanoplanktonguy. When do you expect that Earthlings will actually get access to rock specimens from the Martian surface to do routine geological research? Do you think that most of that collection and analysis will have to wait until humans occupy Mars?
No, there's a plan. NASA has plans, and there are pretty well advanced plans for bringing back Mars rocks. In fact, the next generation of Mars missions, beyond the one that's headed on its way there now, is going to start the staging process. And in fact, the Mars rover that's headed to Mars right now is part of its mission is to set aside samples to pick judicious rocks and stage some samples that will be the subject of a subsequent landing expedition to bring back those samples. So this is already underway, the plan to bring back samples with the very next Mars rover. The time scale for that subsequent mission, or series of missions actually, to bring back those rocks is a little uncertain. It's not less than 5 or 6 years, and maybe not more than 8 or 9 years. So somewhere in that time frame, I think we will actually start to get Mars rocks back into the lab on Earth, which would be very exciting.
The next question is from Zakaria 93 or 0093. Is there any coordinate system of the universe with reference to the point where the Big Bang occurred?
No, there's no coordinate system for the universe in the sense of a normal coordinate system, which has a 0 and then an axis or multiple axes that increase numerically. Because to do that, you'd actually have to identify a center. And there is no center to the universe. All we can do is measure a coordinate system with reference to expanding space-time. And it's a uniform expansion, which means the degree of expansion per second or per year for any unit of time is the same anywhere you are in the universe. And therefore, there's no way to identify a coordinate system 0 point. You can identify the coordinate system expansion rate, and that's the expansion rate of the universe, but that's the best you can do.
I want to address, so we talked about eyepieces through a telescope, professional telescope earlier, and I guess the real point of the question, which I misunderstood, was is there a particular design of eyepiece that professionals would recommend using? Orthoscopic, Plossl, Kellner, Erfel, or et cetera.
Right.
But again, part of the problem is that professionals don't use that many eyepieces.
Yeah.
But I'll let
I
you
mean,
talk about it.
Yeah, so really professional astronomers rarely use eyepieces on any telescope larger than about 1 meter. They're just essentially not used because it's far more efficient and more reliable to have a CCD camera. And that's even not just the camera that takes the data, but also a guiding telescope is using a camera, and a telescope that looks at a larger field of view to look at the weather or to localize your pointing of your telescope. These are all using CCDs too. So essentially everything has now been given over to electronic detectors, and the eyepiece doesn't play a role. In amateur astronomy, of course it does. And in addition to the names mentioned, the Barlow, the classic Barlow lens, that was probably the first and most popular set of lenses that amateur astronomers use and still use, I think. Those are very mature and robust technologies, not even that expensive. But the professional world simply doesn't use eyepieces in general.
All right, the next question is from Cosmic Katie Katie. How are we able to see objects moving away from us faster than the speed of light?
That's a good question. We couldn't actually see a particular object moving away from us faster than the speed of light, because nothing can go faster than light, and therefore that light would never reach us. But we look at objects as they were, not as they are. And so what can happen is we can see a light from an object, we can see the light from an object that at the time that light was emitted was moving away faster than the speed of light from us, but subsequently the universe expansion slowed down, allowing that light to reach us. Now that sounds like an unusual or weird circumstance. It's actually completely standard in cosmology, because the universe has decelerated for the first 2/3 of its history, the first 8 or 9 billion years. And so indeed, any 2 points in space-time were moving away faster than light from each other for the first roughly 1/3 of the universe's history. And so we can easily see objects, and we see many galaxies and quasars in that first 1/3 of the universe's age. That's quite easy to do with any large telescope. So we have hundreds or thousands of objects that are seen that far back in time and that far away. And all of those objects, when that light was emitted, were moving away faster than the speed of light from us. But the subsequent deceleration has allowed the light to reach us and be measured by our telescopes. So it's actually quite a routine thing to see this phenomenon.
The next question is sort of related, but PB Sahu 11 would like to know what is there or what's that moves faster than energy?
Well, in principle, in relativity, which is still a very robust theory of physics from Einstein, the speed of light is an absolute limit. And so neither mass nor energy can move faster than light speed. Light is energy, obviously. It has an equivalent mass if we want to think of it as a photon. But nothing can travel faster than that. And so far in physics and experimental situations in labs around the world, nothing has been shown to violate this very strong principle of physics.
The next question is from Speed of Dark blog. Is it true that Kepler data suggests every star we see in the night sky hosts a planet, and about 1 in 5 stars hosts an exoplanet?
Yes, it is true. We expect, and we have good simulations to back up this supposition, that it is a natural process to form planets as stars form. And so we would expect planetary systems around us, almost all stars, or most stars. And the data from Kepler, which you remember is the nearby part of the galaxy within a few thousand light years, galaxy is 100,000 light years across, so it's our backyard, has pretty reliably shown that with the sensitivity that Kepler has, essentially every sun-like star has at least one planet, an average of one planet. It's also shown that stars that are not like the sun, like dwarf stars, tend to have one planet per star. So there are at least as many planets in the Milky Way galaxy as there are stars. And that number, of course, is huge. It's 300 or 400 billion. And that's how many planets there are in the galaxy, at least. And the true number, given limited sensitivity of Kepler, is probably trillions of planets in our galaxy.
Excellent. The next question is from Murray, Switzerland, who would like to know over what period of time does an event like a collision of neutron stars or black holes take place?
So collisions of compact objects like neutron stars and black holes, the overall timescale can be very long, hundreds of thousands or millions of years, because they are going to do a very slow gravitational dance where they are in orbit around each other in a stable orbit. The reason that orbit will not stay the way it is, however, the reason it can't be stable for hundreds of millions or billions of years, is the fact that the gravity is so strong that some energy is lost from the system by the radiation of gravitational waves. So the slow conversion of gravitational potential energy into gravitational radiation energy or gravitational wave energy takes energy from the system and causes the objects to inspiral. And so they are going to gradually come together. And that inspiral is essentially an accelerating process. And so there's a crescendo in this process, which starts and takes tens or hundreds of thousands of years, where in the final years or so, the inspiral is accelerating and the amount of gravitational radiation is increasing. The actual merger phase is very quick. So the actual physical merger of the two black holes from the time their event horizons essentially touch to the time they merge together and oscillate into a stable configuration, that's seconds. And typically the chirp or the gravitational wave signal for the peak of that merger process takes less than a second, some number of milliseconds. So it's an incredible process, which overall is taking a long period of time, which in a crescendo, all the real action that leads to the gravity waves we've detected happens in less than a second.
The next question from one of our live participants is from Aquarius Francine. Since Newton's time, new math was created to deal with complex calculations and our new understanding of the universe. Is there new mathematics being created currently by astronomy?
Yes, that's an interesting question. And indeed, not just in astronomy, but in science in general, and particularly in physics, new mathematics has often been created to solve problems or to address situations that we don't understand well enough. Newton himself, of course, developed the calculus in a way as a way of calculating the gravity of three-dimensional objects, which you couldn't really do with other methods. His version of calculus using fluxions, as he called it, actually proved less sturdy and less flexible and less friendly than Leibniz's version of calculus, invented around the same time. Newton had a bitter feud with Leibniz over who invented the calculus. Well, they both did, using different methods. But it turns out that the Leibniz method is the one that we learn in school now. It's the one that dominated. But that was a classic example of an entire field of mathematics being invented to solve a problem in astronomy or astrophysics. And this has continued in part. It's rare to invent an entire field of mathematics to solve a physical problem, but there are some fields of topology, or the mathematics of shapes and shaped surfaces and curves and multidimensional spaces, that have been used to understand string theory, for example, or the early universe. So that's another example. And it is indeed the case that mathematical methods are still being developed to understand certain fields of science.
Excellent. The next question is from Mark STO. Is it possible to one day build an anti-gravity device?
It would be interesting. It's a great science fiction concept and very favored of science fiction writers over the years, to have a device that could counter gravity. No such device exists, and nor is there any idea of a physics-based technology for countering gravity. So at the moment, the answer is no. But I don't think we can close the door entirely on that possibility, because our technology really is quite primitive as humans. We've only had advanced technology for roughly a century, maybe since we've had computers. So gravity is the weakest force in nature, and maybe that could give us optimism that it's not an impossible force to counter. Nature has provided something called dark energy, which works essentially as anti-gravity, because it goes in the opposite direction of the gravity that would be making the universe expand slower and makes the universe expand faster. So on these very large scales, we've already found a physical entity that essentially acts like anti-gravity. But we haven't found an entity or a mechanism or a tool that we can subject to our will and create a counter to gravity on scales of our choosing.
All right. The next question is from one of our live participants who would like to know, Smayana Twitch would like to know, how is antimatter detected?
Antimatter is detected in the way that normal particles are detected, like at high energy physics institutes like CERN and so on, by their interactions with normal matter. Since antimatter is very rare, all we need to do is look at the point at which an antimatter particle meets its normal matter twin and produces gamma rays, and then you have detected the antimatter. So actually antimatter is really easy to detect, because in normal physical situations it will run into matter and create gamma rays. And the energy of those gamma rays tells you what kind of antimatter particle you were dealing with. Now, in the very original physics of the 1930s and 40s, when antimatter was predicted and then detected, this was done with cloud chambers. It was done with very low density situations where supersaturated mist or fluid was injected. And as the density was lowered in this medium and the mist was supersaturated, then any particle traveling through the fluid in the presence of a magnetic field would have curved trajectory. And that's how the positron was first detected. That was first detection of antimatter, because the positron in a magnetic field showed the opposite curvature to an electron. So that was, for example, the historical way that antimatter was detected. But now it's detected in controlled situations where it interacts with a very low density of normal matter particles, of which you know what they are, and therefore you can say from the energy that's released what the antimatter particle was.
Theo Bernasconi, 123, would like to know, do you believe in alien life living on planet Earth?
I don't. I've been swept into a large discussion because I wrote an article in The Conversation, an online periodical that scientists and other academics write for. And I wrote an article about UFOs maybe foolishly, essentially saying that it was not ridiculous to have the possibility of UFOs, because astronomers do think there's intelligent life somewhere in the universe, that we're unlikely to be unique. But most astronomers don't believe it's already visited here or is living here already. And my article was about that. It generated a lot of comments, 400 or 500 comments. I lose count. So I understand there are many people out there who do think aliens have visited, and some who think aliens are already here, and some who think it's being kept secret by a conspiracy, which is a classic conspiracy theory, of course, very hard to rebut. I don't think aliens have visited, and I don't think they're living here, and I don't think they visited and people are keeping it a secret. I think it's too big a secret to keep, and I also think that the evidence would have made its way into the realm of scientific inquiry, and the scientists should have been able to scrutinize this evidence and be able to say whether it's valid or not. It's just too much of a conspiracy theory to say that somehow it's been happening and we don't know about it, or scientists don't know about it, or there's no way to verify it. That's a little too convenient, and it takes it out of the realm of science. So no, I guess I don't believe in that.
Aman Preetgala would like to know, I want to know how close we are to realizing the dream of extraterrestrial mining for resources.
I would say space mining is maybe 15 years away. That would be my best guess if I had to hazard a guess, because the technologies to do it are approaching quite quickly. NASA and other space agencies have already demonstrated our ability to send spacecraft to asteroids, comets, objects that might have, resources we would like, metals and rare earths and so on. Asteroids are the best example. We've shown our ability to reconnoiter with such objects and land on them, and it's a very small step from being able to do that to being able to tether in them and use rockets to slightly alter their trajectories. And in that case, you have the technology to take what would be a near-Earth object and bring it into a captured Earth-Moon orbit. It's much harder to bring it into a full Earth orbit because the object would have to lose too much energy. That's too hard to do. So we can create the space resources. We can take them from the inner solar system where they come close to the Earth and capture them, and sort of quasi-capture them in an Earth-Moon orbit. That technology already exists. And from then we just have to mine them in situ, have to set up a mining operation in a way to get the material down to the Earth and not make it so expensive that it was not a viable proposition. Now the expense of getting the material down to the Earth is really the kicker. And so I think that's the thing that will keep this into the fairly distant future, i.e. more than a decade, because otherwise we could be doing this in a few years, or some corporation with billions of dollars to invest could be doing it quite quickly.
Prab 1307 would like to know, what is Cherenkov radiation, and is the speed of Cherenkov radiation more than that of light?
Yes, when particles, high energy particles, relativistic particles interact with a medium, they essentially release Cherenkov radiation, which is light. It's electromagnetic radiation, which creates a pulse where in a low density medium, it's momentarily faster than the speed of light. So it's a sort of it's not violating relativity because of the density of the medium. But it's a standard interaction of high energy particles with a fixed medium, and this radiation is used to detect those particles. So it's a standard method of detecting, for example, cosmic rays from space by this Cherenkov radiation. The trick is that the instantaneous velocity can be faster than the speed of light, but the signal velocity or the phase velocity or the velocity with which information is carried is never exceeding the speed of light. In the same way that you can imagine information traveling faster than light, if you shone a beam on the moon, you could track it across the moon's surface such that light was moving across the moon's surface faster than light speed, but information is not being carried from A to B by that process.
The next question is from PB Sahu 11. If there's nothing faster than light, then why is it that black holes can attract light?
So I would say it's not necessarily that black holes attract light, it's that black holes retain light. They do not allow light to escape. Remember, a black hole formerly was a star, and the star was emitting radiation, and that star had a mass, and so the light was escaping from a massive object. When that dead star collapses, it eventually reaches a state where the escape velocity at the surface is the speed of light, and at that point the light can't escape. So it's not necessarily that the star is attracting light, it's retaining light or not allowing anything to escape. Now, it is true that a black hole has a region called a photon sphere, and that's twice the Schwarzschild radius is essentially operationally the radius of the event horizon. At twice that distance, you have something called the photon sphere, and that's a region radius defining a circumference at which a photon could be trapped in a circular orbit around a collapsed star. And so in that sense, you could trap light. If you had a light beam that tangentially approached a black hole and hit the distance of the photon sphere, it would be trapped into a circular orbit. So that's the very particular way in which light might be hypothetically trapped by a black hole.
The next question is from AZ Harks 98. Do you think that human beings will become an interstellar species in the next 100 years?
I would say 100 years is a lower bound on that. It's a very challenging thing to do. I think eventually, yes, we will become an interstellar species if we survive at all, which is up for grabs, I guess. The business of being an interstellar species is extremely challenging because recognize that the distance to the stars is hundreds of thousands of times the distance to the planets. So we can explore in the solar system with space probes or with humans going even into the outer solar system. We can plausibly do that within a few decades. But to go to the stars is hundreds of thousands of times further, so it's hundreds of thousands of times more difficult. It's either going to take hundreds of thousands of times longer at the speeds we can attain with our spacecraft, which means humans would have to be sort of put on ice or in suspended animation. That's a technology we don't have so far. Or they would have to be accelerated to a significant fraction of the speed of light, maybe 5% of the speed of light. And the energy requirement to do that is phenomenal. It's more than the energy requirement of the entire Earth for a year to accelerate a normal spacecraft with a few people on board to 5% of the speed of light. I think that's a good round number. So this is really challenging, and these are the reasons why interstellar travel is probably not viable on a timescale of a century, a few centuries maybe. I think it'll happen, but we're going to need some technologies that we don't yet possess for this to happen.
All right, we want to thank Lauron.com for subscribing. This is going to be our last question for today. I want to make sure that I understand it, so maybe FX35 can correct me if I misunderstand. They'd like to know if there's a way to calculate a celestial object's luminosity based on nothing but its brightness data. So can you calculate its luminosity from absolute bolometric magnitude?
Just brightness alone is not typically enough to tell you the luminosity of an object. I mean, to get luminosity, which is intrinsic brightness, which really means how many photons per second are being emitted, you have to know the distance as well. So typically there are three things that are interrelated, where if you know any two of them, you can get the third. Well, one is the apparent brightness or apparent luminosity. The other is the absolute brightness or true luminosity. And the third is the distance. And they're interrelated by the inverse square law. So typically measuring the apparent brightness of something is not sufficient to infer its absolute brightness unless you know how far away it is, with some exceptions, however. And the exceptions are if the nature of the object, and not just its brightness, but perhaps its spectrum or some other aspect of it, tells you what kind of object it is intrinsically. For example, a supernova type 1a, which is a standard light bulb in the universe, then you can know how bright it really is because you know what type of object it is. But typically, stars are extremely variable in their brightness. They vary in brightness, intrinsic brightness, by factors of millions. And so just the apparent brightness of a star is almost no indication of its true brightness. Okay, thanks for that question for all of them, and for a good variety as usual. And we'll be announcing our next 2 sessions soon. So thanks for participating. Thanks to Matthew and Vicky for facilitating.
Excellent. Thank you, everybody, so much for joining us. Thanks to those of you who followed us and to our new subscriber. We really appreciate it, and we're looking forward to our next live session.